Hello friends, in this video let's look at this interesting problem related to work done. So let's see what's going on. An object of mass m is being pushed slowly using force F, which is always tangential to the ground. Now this object is being pushed up a hill whose height is h and the length is L. So you can see that the surface is irregular. And the coefficient of friction between the object's surface and the ground underneath is mu here. So what is asked is, what is the work done by this force F when the object climbs the hill? So when it goes from here to here slowly, what is the total work done by this force? Let's solve the problem. Let's take a small segment of the object's movement. Let's say the length of this segment is ds. Let's say this length makes an angle theta with the horizontal. So this line segment is along the horizontal, so we can call it small portion of the length L, dl, and this line segment is along the vertical, so we can call it small portion of the vertical height, dh. And now as this object is moved along this small length using the force F, let's figure out what is going on here. So we can draw the free body diagram based on this. So this is the object of mass m. mg is the gravitational force. There is normal reaction n. There is frictional force, let's call it small f. And there is F. This angle is theta. We have been given that the object is moving slowly, that there is no acceleration. So the component of the gravity towards the hill is mg cos theta. So n equals mg cos theta. We also know that force of friction equals mu n. Therefore, friction is mu mg cos theta. As the object traverses this small distance, there is work done on the object by the force F, by the frictional force, by all the force. As the object moves the distance ds, we have work done by the force capital F, and this is a small portion of the total work done. So dwf is equal to F times ds. So this is the dot product of so F work done is dot product, and because both the vectors are in the same direction, so it's a simple multiplication of Fn, the quantity F, and the quantity ds. Similarly, the small work done by the frictional force is minus F times ds, because the direction of friction and the direction of the displacement are opposite, so hence the minus sign, cos of 180 degrees, and the quantity is multiplied. So therefore dwf is, we know that F is mu mg cos theta, so minus mu mg cos theta times ds. So let's look at this triangle. Cos theta is nothing but dl by ds. Cos theta is dl by ds. Note, because we had considered a very small portion of the object's total movement, we can treat this as a straight line, and hence we can treat this as a right angle triangle. So cos theta is dl by ds, and therefore dl equals ds cos theta. So we can use this to say that d of the small work done by the force of friction equals minus mu mg dl. So this is one important result here. Let's keep marking the important results. The small work done by force capital F, the small work done by force small f, which is friction. So what are the other forces? There is normal reaction. So the small work done by normal reaction is 0 because the normal reaction and the displacement are at 90 degrees to each other, so the dot product is going to be 0. Okay, and there is one more force there, which is the force of gravity. So the small work done by gravity equals, let's for dwg, let's draw a diagram. So this is the object, this is angle theta, this is mg, this is the component of gravity along the direction of ds, which is mg sine theta, and this is the direction of ds. So all right, so this gives us very clearly that small work done by the force of gravity is minus mg sine theta times ds. All right, consider this object as the system under investigation over this movement. Then the total work done on this object is equal to the change in kinetic energy of the object. So total work done on m over ds equals change of kinetic energy of m, which is 0 because we are told that object is moving slowly, there is no acceleration. So we are going to say that change in kinetic energy is 0. So this implies that, so dwf plus dwf plus dwn plus dwg equals 0. We replace the values. So f ds and then minus mu mg dl. So f times ds, well, we can leave the term for dwf as dwf and then replace the term for work done by the friction, which is minus mu mg dl. So minus mu mg dl, this is 0, and this is minus mg sine theta ds, and this is equal to 0. From the triangle we can see that ds sine theta is actually dh. ds sine theta is dh. So this implies that dwf equals, take these two terms to the right hand side, mu mg dl plus mg dh. This looks extremely promising now. So if we integrate both the sides, dwf, so total work done by the force when the movement started is 0, and when the total work done by the force F as the object has climbed the hill is what we require, which is wf, equals mu mg integral of dl 0 to L, which is a given quantity, plus mg integral of dh 0 to h, which is a given quantity. So this implies that wf equals mg times mu L plus h, and this is the answer. Let's recap quickly what all we did. So we were given the problem. We considered the motion over a small, very small, infinitesimally small part of the hill. We assumed that the motion in that very small part is a straight line, making angle theta with the horizontal. So sine theta is dh by ds and cos theta is dl by ds. Then we looked at the free body diagram, and then we saw that normal reaction is obviously mg cos theta. So force of friction is mu mg cos theta. And then we said that, so d of wf, the small work done by the capital force capital F was fds. What was more interesting was this, which is the small work done over this small movement ds by the force of friction is minus fds, which is minus mu mg cos theta ds. And then we replace the value of ds cos theta, which is dl, So the small work done by force of friction came out to be mu mg dl. Then small work done by normal reaction was 0 because normal reaction and the movement are at 90 degrees to each other. So no work done by the normal reaction for that movement. And the small work done by gravity was minus mg sine theta dx. And then we applied this principle of physics, which is total work done on the object over that distance will be the change in kinetic energy. And because the object is moving slowly, there is no change of velocity, and hence change in kinetic energy is really 0. So then we simply substituted all the terms. Total work done is work done by these small work done over that small period. And the net result out of this is supposed to be 0 based on the physical principle. Now we substituted the values, and that gave us this equation, and then we integrated it over the total movement. This represents the total movement over the entire hill. So work done at the start of the hill is 0 by the force capital F, and at the end of the hill is what we need to calculate, so W capital F. And when we integrate this expression, the variable is mu, m, and g are constants. dl is what varies over 0 and L. And when we integrate this expression, m and g are constants, and dh is what varies from 0 to h, which give us this nice answer. Thank you.